Okay, this is the very last page on your 11.1 notes.
Are we just getting a new package on that, or are we going to do something?
Yeah, we're going to get a new notes package. So that's the third thing I'm going to hand you today. Fourth, technically, but that's fine. A candle is burned for several minutes, just like you burned a Dorito, right? Or you burned whatever. So a candle is burned for several minutes to heat a can of water. The temperature of 100 milliliters of water changes from 16.4 degrees Celsius to 24.2 degrees Celsius. What is the enthalpy change? Now remember, the enthalpy change of the water, is the exact same thing as the enthalpy change of the candle. Does that make sense? Any energy lost by the candle, we need to assume that all of it is gained by the water, because this is some sort of a calorimetry experiment. So what is enthalpy measured in? Do you know? Joules. Do you see joules here anywhere?
No.
Ah, son of a gun. But we have water, and we know how much energy it takes to change the temperature of water, right? So we're looking for enthalpy, that's delta H, and it's measured in either kilojoules or joules, whatever, it doesn't matter. It's all the same thing. Okay, I want to be super clear about this. I'm going to kind of switch it up just a second, just like a little tiny bit. 4.19 joules per gram degrees Celsius. If instead of joules, I could get kilojoules out of this. As long as I could get kilojoules out of this as long as I measured the mass of the water in kilograms. Does that make sense?
Yeah.
So we could turn 100 milliliters into grams. What is 100 milliliters in grams?
100 milliliters.
It's 100 grams. But what is 100 grams as a kilogram? Yeah, so if you're not good at metric conversions, this is going to be tough, right? Does anybody need me to go over how to convert between grams and kilograms? Okay, well, just let me know. So this is 0.100 kilograms of water. And what was the temperature change between 16.4 and 25.2? 8.8 degrees Celsius. Over 1. You don't have to put over 1, but I do. Yeah, I want to show you this because I want you to keep it in mind, because sometimes we have to cancel out kilojoules, and so this will be a good way of doing it. Yeah. It's just that your answer is going to be 1,000 times bigger because it's in joules instead of kilojoules. Yeah. That's all. Okay, what'd you get? What'd you get?
3.69.
3.69 kilojoules?
Yeah.
Perfect. Anybody else get that? Okay, that's wrong.
Yeah, isn't it the 8.8?
Good. 2 significant digits, right?
Wait, but that's not,
Okay.
Oh, it's already rounded once already.
that's not in the text. That's not in
Yeah, so
the
it's 3.6.
text has 3 significant digits. So if you just make up your own significant digits, you can't do that.
When you put 0.80.
Would it not just be?
Isn't it whatever you use in your equation?
No.
No. Okay. This is a great problem for us to have right now. I want to be very clear. There are 2 significant digit rules that you should have known from grade 10 and grade 11, now in grade 12, or now in at least a 30 level subject, is that when I multiply and divide, when I multiply and divide, it's the lowest number of significant digits. But when I add and subtract, I have to take the lowest number of decimal places. So let's think about it this way. If I went 25.2 and I subtracted 16.4. When I do this subtraction, there's only a difference of 8.8, not 8.80. Do we know, is this 0? Do we know what digit this is?
No.
No, we don't. So our actual information is truly 2 significant digits. Now here's the deal. On a proper assessment like the diploma exam or a unit exam or something like that, the question will always say, write your 3-digit answer in the box or whatever. Right? So it will always tell you 3 digits or 2 digits or 4 digits or whatever. Is that okay? It will always tell you that. Here, yeah, I understand we're using a rule that you probably haven't thought of in a really long time, but this is properly 2 significant digits. 3.7 kilojoules. Now, if this was 16.40 and 25.20, then it would be 0 minus 0 would be 3 significant digits, right? When you put this into your calculator, just because your calculator spits out 8.8 doesn't mean it's not 8.80, it just doesn't give you the 0. Yeah, Shelby.
Okay, so you said for numerical we would have to write 3.69 because it would ask for the 3 significant digits?
No. I'm saying the question will tell you how many significant digits I want you to have. So it will specify. I'm not saying this question will ask you for 3 digits. I'm saying a question will tell you exactly how many significant digits for that specific question.
And if it was in, then you would expect like the 3.7.
If this was 2 significant digits, yeah, I would say 3.7.
Okay.
So your answer would be 3.7, right? Yeah.
If it was like multiple choice.
If it was multiple choice, I would never give you 2 answers that were rounded to different significant digits. I'm not testing you on significant digits. What? No, the diploma exam will not. The diploma exam will never test significant digits in a multiple choice question. And then in numeric response, it will always tell you how many digits it wants. So realistically, it's never going to ask you. It's never going to test you on significant digits. Realistically, it just can't. Okay, Kate. Shh. Listen up. What does that mean? How much energy did the water gain or did the water lose energy here? Think of the context of the situation. Did the water gain or lose energy? If we have a candle and we have that's a flame, whatever, deal with it. And we've got a cup, and there's some water in here. Is this water gaining or losing energy? It's gaining energy. And what's happening to the candle? Something is gaining energy. Something else has to be losing energy. What type of energy is being gained by the water?
Translational.
So otherwise known as kinetic energy. We don't know, Max. We don't know. We don't know if it's translational, rotational, or vibrational, but the combination of all 3 of those things gives us kinetic energy. Okay? So something can have a buttload of rotational energy, and something else can have a buttload of translational energy, but they can have the same amount of kinetic energy, and it relates to the same thing in real life. Okay? So we're gaining kinetic energy. What is the candle losing? Is the candle wax getting colder? No. Is it getting? I want to be very clear about this.
It's not getting hotter.
Is it getting hotter? No, it's not getting hotter. Okay. The candle wax itself. I agree. The flame is imparting heat onto the candle wax at the top, but the candle wax is not getting hotter. So this thing is not gaining or losing any kinetic energy. It must be losing potential energy, right? So how much potential energy did the candle lose? 3.7 kilojoules. And we measured that. Did we measure directly the amount of energy lost by the candle? No, but we inferred that the energy gained by the water is the same as the energy lost by the candle. Because we're in an isolated system, right? There's a difference between a closed system and an isolated system. Chemical reaction has an enthalpy change of 4.8 kilojoules. If all this energy is absorbed by 120 milliliters of water, that starts at 21 degrees Celsius. What will be the final temperature of the water? Go ahead, try this out. We're using unit analysis. All you have to figure out is what do we want? That's it. Max, did your hand go up?
Yeah.
What? No, we're going to talk about what that equal sign means here in about 4 minutes. I'm going to walk around handing something out, but it's just our newest notes package, so you don't have to do anything with it right now. Yeah, Logan, you want what? Okay. Your units are not set up. But, okay. Yeah, take the first one. Negative.
Celsius.
You really what you have to do. This isn't a lead.
Cause I gotta make sure no one fucked with it. Here's this one. Pink. Pink always works. Dude, I don't even like how did I'm gonna steal that charger. Isn't it?
Oh, okay. And then
Can you buy a charger off me? No, you can rent one if you want. I know, for free.
that's right.
And you like it?
Yeah.
You can buy your own.
Where'd you get it?
Amazon.
Amazon.
Yeah.
I'm not gonna wait to deliver. Pay for shipping.
Get right.
Amazon. Well, so now I'll do an auction for it.
No.
And I'll be the only bidder. And if you say no, then I will get it for a discounted price of $0. That 21 Celsius is even. Is it?
What is the
What else do you I'm not going to treat myself better than I do.
Okay. Yes, everybody wants to go staple it, and that's totally fine. But just quietly. So a chemical reaction has an enthalpy change of this much. If all the energy is absorbed by 120 milliliters of water at 21 degrees Celsius, what will be the final temperature? What I want to know, what I'm curious about, is what do you want out of this? You want final temperature, but in general, all you care about is the temperature change right now. Would you agree? If you knew the temperature change, then you could just add it or subtract it to your temperature. So we're looking for the temperature change in degrees Celsius. Yes, I agree. The question has degrees Celsius in here. But what else has degrees Celsius?
The ratio of 4.1.
The water, right? And so remember, if it's giving you kilojoules, well then we can just do kilograms, right? So 1 kilogram degrees Celsius, 4.19 kilojoules. So it still takes 4.19 kilojoules for every kilogram to raise it by a degree. And so what are all the units that we have to cancel out? kilojoules, 4.80 kilojoules, and kilograms, right? So 0.120 kilograms. Calm down. It'll be okay. Calm down. Everybody. It's okay. Now, what I want to bring your attention to is that there's a context, there's a contextual piece of information in here, and we need to look at it from two different perspectives. Okay? Denver, do you want to stand up here and be my partner in crime? Is that okay?
Yes.
Do you want to be the chemical reaction, or do you want to be the water?
I'll be the water.
You want to be the water? Okay, calm down. Shh. So, if I'm the chemical reaction, read the question. Is the chemical reaction giving away heat, or is it absorbing heat?
Giving away.
The chemical reaction is giving away heat. What's surrounding the chemical reaction?
Water.
Water. So the chemical reaction is giving away heat. Oh. I know, I didn't want to warn you, okay? The chemical reaction is giving away heat to the water. Would you agree?
Yes.
Yes. So as the chemical reaction gives away heat, what's absorbing heat? The water. Do you agree there's two different perspectives?
Yes.
From the chemical reaction's perspective, am I losing energy or gaining energy? I'm losing energy. Is the water gaining or losing energy?
Gaining.
It's gaining energy. Are we okay with that? I need. Sorry,
Take your energy back.
Okay, so from the water's perspective, is it gaining or losing energy? It's gaining energy. So is this going to be a positive temperature change or a negative temperature change?
Positive.
Positive. It's going to get heated up, right? So its temperature is going to increase. How much is its temperature going to increase by?
9 point.
Did you do it?
Times 10 to the negative 5.
9 point what?
5.
9.55 degrees Celsius.
No. Oh, okay. Kilojoules, yeah.
Kilograms, kilograms, kilojoules, kilojoules, and we're left with degrees Celsius. Okay, now here's the problem. This question is just not very well thought out. That's the problem with this question. Let's assume that this is 21.00 degrees Celsius. Is that okay? Starting out at 21.00. So let's add 9.55 to that. So the final temperature, T final, is going to be 21 plus that, so 30.55 degrees Celsius. Is that okay?
No.
That is so.
I just have to switch the sequence in here.
What do you mean?
Change it to 0.00.
Just because I wanted to take into account both the decimal places. Because okay, all right, whatever. Let's not do that.
I just
Okay, let's not do that.
I want to do something.
No, whatever. So let's add 9.55 to this. You still get 30.55, but what do we have to round to now? You have to round to 31 because we need the nearest whole number. 31 degrees Celsius. Whatever, it's whatever you want. Okay, Max.
If I changed the kilojoules to joules and I kept the ratio as joules and grams,
Yeah, that's totally fine. If you because this would be 4,800 joules and this would be 120 grams, and it's still the same ratio. They're equivalent fractions, right? So it's whatever you want as long as you do it properly, right? It doesn't really matter. Okay, does anybody have any questions about that? Shelby.
Okay, this might sound stupid, but why are you adding the Celsius at the end and not putting it into your equation?
Because this represents the temperature change.
Right.
So when I add this much energy to this much water, it gains, doesn't matter what temperature it starts at, it will gain a temperature or increase in temperature by 9.55 degrees Celsius.
Okay, so like regardless, we're still trying to.
Yeah, you want to figure out the final temperature, but in order to know that, you need the initial and whatever temperature change. What if we started at 1,000 degrees? And then it would be 1,009 degrees now, or 1,010, whatever. Does that kind of make sense? When I add this much energy to this much water, it doesn't matter what temperature it starts at, it will increase in temperature by this much. So you have to figure out what the initial temperature was and then add it. Is that okay? Cool. I am gonna scooch, and we're gonna start talking about your new notes package is 11.1b. Okay. We have about 40 minutes, 45 minutes to talk about the molar enthalpy. I think we can do it if we just kind of buckle down. I want to get you doing some practice questions by the end of the class. The entire idea behind molar enthalpy is it's the exact same thing as molar mass, kind of. Molar mass represents how much mass in every mole of that substance. But that's like a physical property of that substance. It just represents how much mass is being occupied by this many molecules. Molar enthalpy, remember, enthalpy just means what again? Change in energy, right? So this is the change in energy per 1 mole of that substance. That's all it means. We're still using unit analysis. Except this time, instead of getting enthalpy, which is in kilojoules, I want you to look at your data booklet, tell me what the units are for molar enthalpy.
What page is that on?
It's on page 2 of your data booklet. It's the first page after your periodic table. You want a periodic table?
Delta T8. Oh wait, no, I've lost.
So what are the units for molar enthalpy? Kilojoules per mole, right? Molar enthalpy is all about kilojoules per 1 mole.
Yeah, oh, I just had a symbol.
Ah.
I have 2 for some reason.
Okay. I want to be very clear. The molar enthalpy of a reaction is very specific to a certain reaction. So, for example, we could talk about a specific compound. I don't know. Let's talk about the compound oxalic acid. Whatever, doesn't matter.
That's the same coordinate.
Yeah, it's a palindrome, right?
Right, race car.
Like race car. And the sentence
Rats.
Able was I ere I saw Elba.
Huh? There's another
Huh?
one talking about.
Oh, all rats have stars. Rats?
What? What?
No, wait. Wait, I'll think of it, get back.
Anyways,
Oh.
What is that?
No.
It's backwards.
has anybody ever heard the sentence before? Able was I ere I saw Elba?
No.
And is that also
No, Elba is an island in the Mediterranean. Elba is an island in the Mediterranean, and that's where Napoleon was outcast to after the Napoleonic Wars, when he was kicked out of kind of the monarchy, not really monarchy, but the monarchy. Yeah, and then he came back with a vengeance. So,
Also, do geese see God?
Rats. Rats.
Hi, Vsauce, my
Rats. Do geese see God?
Go hang a salami. I'm on lasagna pot. That's fine. What
do geese see God?
does that mean?
A palindrome is the same forwards and backwards.
Rats.
Oh, that was
Rats live on no evil star. Rats live on no evil star.
Oh yeah, okay. Anyways, yeah, tangent. That's a good. Okay, let's try this. No, we're not going to talk about more palindromes. What are they called? Yeah, shut up. Okay, the reaction. Let's talk about this reaction. I could talk about lots of different things in regards to this particular compound. This particular compound is a liquid at when it's pure, it's a liquid at room temperature. Now, I can take this and I can burn it. I can combust this thing. So what would be the combustion reaction for this substance? I would take this, and I would react it with oxygen, and what two things would it make? Carbon dioxide and water. And this reaction would have a very specific enthalpy. And we're going to use a very specific combination of letters to represent molar enthalpy, okay? For formation, how would this be formed from its elements? What elements do we need to form oxalic acid? Nope. We need what? Water. Nope. We need hydrogen, oxygen, and carbon. It's a formation reaction is a very specific definition. We define formation reactions to be something being made from its elements. Now, obviously, this isn't balanced, and I don't care to balance it right now. That's not what I want to focus on. But this is going to have a very specific enthalpy as well. Neutralization, when this thing gets neutralized, right? So that's like this thing. Is this an acid or a base? Acid. It's an acid, so we need a base to neutralize it, right? So NaHOOCCOO plus water. It's going to have a very specific delta H. And the enthalpy of solution, that's when I take this pure substance and I make a solution out of it. HOOCCOOH liquid. How do I make a solution out of this thing? What do I got to dissolve it in? Water. So HOOCCOOH aqueous. Every single one of these reactions is going to have a very specific delta H attached to it. And we're going to use the specific combination of letters to represent what reaction we are specifically talking about. What letter do you think we would use for combustion? C. So what I would say, we want it's kind of backwards. So it's the molar enthalpy of combustion. That's the way you read it backwards. What would formation be? What combination of letters would I use? So the formation, and it's the molar enthalpy of formation, right? Is this fairly straightforward? But it's telling you that this is what we're looking for, or this is what we want, or this is what we have, whatever. So the molar enthalpy of neutralization, and then the molar enthalpy of solution. Because we're talking about a chemical reaction, a positive enthalpy change refers to this system. A positive enthalpy change refers to this system gaining potential energy, while a negative enthalpy refers to this system losing potential energy, right? So we could say delta, I don't know, no. The molar enthalpy of neutralization for something, let's say it's positive 30 per mole. I'm trying to get you to think about something, so just stick with me on this. Okay. Is this chemical reaction releasing energy, or is this chemical reaction absorbing energy? It's absorbing energy. It's gaining energy. Where could it gain energy from?
The atmosphere.
Whatever is surrounding it, right? So if this was an aqueous solution, where would it gain its energy from? The water. Okay? So here, this represents an increase in potential energy. So that means the temperature of the water will go down. I don't, hopefully that makes sense. Something's gaining energy, the other thing has to be losing energy. And the system is almost always surrounded by water, because that's it's something that we have abundantly available, and that's how chemical reactions mostly happen in aqueous solutions. Okay, we went through a lot of information there. That's like a lot of gobbledygook, but we're going to build on that a little bit later on. Can I move on? Yeah? Okay. So, by way of an example, butane has a molar enthalpy of negative 2,043.9 kilojoules per mole. What we want to know is how much energy is released when 10 grams of butane is combusted. Now let me think about this for a second. Is this a stoichiometry problem? Is it giving you one substance and then asking about a different substance? No, it's not. So because it's not stoichiometry, you don't need a chemical reaction right now. Okay? I want to be very clear about that. You don't need a chemical reaction. It's talking about one substance, and you're sticking with that one substance. So we can just use unit analysis. What do we want out of this question? We want energy, and energy is always measured in either joules or kilojoules. Read the question. Does it say we're heating up water? So you cannot look at the specific heat capacity of water. Is there kilojoules anywhere else in this problem? Yes. So we're looking for the enthalpy change, not the molar enthalpy. We're looking for the enthalpy change measured in kilojoules. Well, we know every 1 mole of butane releases how much energy when it's combusted?
Negative
2,043.9 kilojoules over 1 mole, right? And because it's talking about the butane, I will put the negative in there. This is from the butane's perspective. Okay, well, what's the only thing I have to cancel out here in order to get kilojoules? I have to cancel out moles, right? Do you know anything related to moles of butane?
Molar mass.
You know the molar mass. It's giving you a mass, so you need the molar mass. Go ahead and calculate for me the molar mass of butane. Okay, so how am I going to write the molar mass of butane? Should I go 58.14 grams per mole? No. 1 mole weighs 58.14 grams. And what's the only other unit I got to cancel out? Grams. 10.0 grams. So moles and moles, grams and grams, we should be able to calculate that. Ah, yes. Did you do it, Mark? Do you see that? I asked people to put in one teeny tiny calculation. You got to put in 3 numbers into your calculator. People are sighing, they're rolling their eyes at me.
351.5.
352.
351.5 blah 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 kilojoules, right? But what was that?
352.
It would be 352 because we need 3 significant digits.
Wouldn't that 1 mole be considered a significant?
No, the 1 mole is a perfect definition, right? In 1 mole, in exactly 1 mole, there is approximately 54.18 grams, or 58.14 grams. So 352 kilojoules. That's the worst 352 in the world, but hopefully you understand. Okay, and I want to be very clear, the negative and the positive doesn't really mean anything right now, because it's asking you how much energy is released. Yeah, we're saying it's released. Okay, sure. But you could have just given me the quantity, and I'm asking you how much is released, and so a positive value would have been fine as well. As long as you understand negatives mean released, positive means absorbed. A student dissolves 21.3 grams of sodium hydroxide in water, and it released 541.2 kilojoules of energy. What is the molar enthalpy of solution for sodium hydroxide? So what are we looking for here? You're looking for the molar enthalpy of what? Of solution for sodium hydroxide. And what is that measured in? What is molar enthalpy of anything measured?
Joules over grams.
No. Kilojoules per mole. A molar enthalpy is how much energy is either released or absorbed per mole of that substance. Okay, do you either have moles or have kilojoules? Do you have either of those things?
Yeah.
You have kilojoules. Where do you want to put them? Top or bottom? Top. Okay. So 541.2 kilojoules. Yeah, over 1. Now we want moles on the bottom. So in 1 mole, how many grams is there?
Whoa, exactly. Which then you.
What was that, Preston? Oh, I thought I heard you say something. No, I thought it was an impression of somebody. Oh. Okay. Hey, so far? What do our units look like? What are our units so far? Have we canceled anything out? No. So we have kilojoule grams per mole. What the hell is that? That's nothing. So what do we have to do? We have to cancel grams, right? 21.3 grams of this stuff. Grams and grams cancel, then we have kilojoules per mole. So what's the answer? 1016.338. Yep. Yeah, it doesn't matter. Whatever. Yeah. Okay, so kilojoules per mole. There is. Okay, stop what you're doing. Look at the board. Straight up stop what you're doing and look at the board. There are 2 reasons why this is the wrong answer. No, don't say them out loud. I want you to just take 15 seconds. There's one obvious reason why this is the wrong answer. Okay? There's one obvious reason. So think of the obvious reason. Sure, awesome. Okay, get it out of your head. There's another reason why this is the wrong answer. I'm going to give you 15 seconds. If you want to talk to your friend about it, that's totally fine. Okay, anybody get it?
No. Yeah.
Natasha? What is the sign on your molar enthalpy right now? It's a positive. Okay, let's go back. Let's go back to the beginning of the question. A student dissolves blah 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 in water and it released this much. That means negative 541. I don't know if you noticed, but I paused I waited a long time after I wrote this value down because I wanted to see if anybody was going to catch that. And nobody caught, and that's fine because we're learning right now. It's not, you're not experts. So this is negative something. Now, what's the obvious answer why this is wrong? Significant digits, right? So we need three significant digits. Negative 1.02 times 10 to the 3 kilojoules per mole. Good? Preston. Yeah. Yeah, that's fine. Any questions? Does anybody not understand why we did that? You very much understand. Okay, well, perfect. Awesome. Okay. A lot of the time, and I would propose that the majority of the time, you are going to see a reaction. You're going to see a reaction, and according to this reaction, the way it's written out specifically here, this is the enthalpy of this reaction. So what I want to ask you, just really quickly, is this reaction releasing energy or absorbing energy? So are its surroundings going to get hotter or colder?
It's absorbing it. The surroundings are going to get hotter.
Okay, the reaction is releasing energy. So if the reaction is releasing energy, is the water surrounding it going to get hotter or colder? Hotter. Now, in this case, there's not really a ton of water surrounding it. It's just air. So the air surrounding it would get hotter. Okay? The molar enthalpy of this reaction for hydrogen is, what I want you to think about, how much energy is being released in this reaction? 290 kilojoules. So, please pay attention. For how many moles of hydrogen do we have reacting here, right now? One. So for every 1 mole of this, we're going to release 290 kilojoules, right? For every 2 moles of this, we're going to release 290 kilojoules. So if we wanted the molar enthalpy of reaction, so the molar enthalpy of the reaction, what's molar enthalpy always in? Always measured? Kilojoules per mole. Kilojoules per mole. Do you see anything to doing with kilojoules in here? Yes. Negative 290 kilojoules. Do you have anything to do with moles of hydrogen in this reaction? It says 1 mole. The coefficient is 1. So over 1 mole. So this is a trivial, you shouldn't need your calculator, right? But what is the answer going to be? 290 kilojoules per mole of hydrogen, right? You don't have to specify hydrogen, but I'm specifying hydrogen so you understand. Every mole of hydrogen that reacts is going to release 290 kilojoules. What about the molar enthalpy of reaction for water? It's kilojoules per mole. So we still have 290 kilojoules being released. How many moles of water are reacting here, or are in the reaction? 2. So 2 moles of water, right? So let's take 290 and divide by 2. Okay, it's just asking for the molar enthalpy of the reaction of this substance. So per mole of water, either used up or made, doesn't really matter. It's just saying, we're making 2 moles, and for every 2 moles, we release 290 kilojoules. So if we had 1 mole that was made, it would only release 145 kilojoules, right? Yeah. I don't know, hopefully that makes sense. There's a lot of us, this class is a lot of us just kind of getting used to the way energy is being given to us or communicated to us, and we're going to have to kind of deal with that a little bit more tomorrow when Mr. Brown is here, because I'm not here tomorrow. Mr. Brown. Mr. Brown. Do you know who Mr. Brown is? That old guy? No. Yes, the old guy.
Old white beard? Oh, that's the guy.
I sure hope he's not watching YouTube right now. He's the mustachioed man. I love Mr. Brown. What? No. Hey, listen up. If anybody makes Mr. Brown's life more difficult than it needs to be tomorrow, I have absolutely no reserves of absolutely raining hell on this entire class.
What if it's just
What? What if it's just one person in particular? Then you need to keep that one person in check. As a class, you need to keep it. Then I will rain hell on that person in particular, as well as the whole class.
You're not a scary person.
What?
I feel like you're not a
He
scary
doesn't celebrate
person.
Christmas.
You feel like I'm not a scary person?
Oh yeah.
Have I ever yelled in? I haven't taught most of you before, but but in grade 9, I definitely yelled at your class. Oh yeah, for sure.
David got yelled at all the time.
Yeah, well, some people get yelled at more than others. But that's okay. Okay, let's put everything we've learned together so far. So again, that context, that idea of gaining energy versus losing energy is going to come into play huge in the following kind of ideas. So let's think about this. Using calorimetry, we can identify the molar enthalpy of a reaction by determining how much energy is transferred to the water, and as long as we know how much of this substance was used up, or how much reacted. So as an example here, this is a calorimetry experiment. We're using a calorimeter, right? Ethanol has a molar enthalpy of combustion of negative 1,366.8 kilojoules per mole. So what mass of ethanol in here is going to be required to raise the temperature of this water by 20 degrees Celsius? What I want you to think about is it's giving me water, but it's also asking me about this substance that's being consumed or reacted. What do you know about the energy lost by this substance and the energy gained by this substance? They're equal to each other. So there's going to be a phantom negative sign that shows up somewhere in this reaction. Okay? What is the molar enthalpy of combustion of this substance? It's negative something. So is the ethanol releasing energy?
Yeah.
Yes. But the temperature is gaining energy, right? So we should be thinking out, because we're trying to change the temperature of the water by positive 20 degrees Celsius, we should look at the water's perspective, okay? So that's fine. What are we looking for in here? The mass of ethanol. Good. We're looking for the mass. And what is mass typically measured in? Okay, grams, and I'm going to say ethanol, so that's C2H5OH. What do you know about the mass of ethanol? Do you see any grams in here anywhere? No, but what do you see about ethanol in here? I see moles of ethanol. So what does that illustrate to you? What do you need? You need the molar mass of ethanol. So let's calculate the molar mass of ethanol. 30. Okay, why? We're going to see very quickly why I wrote grams of ethanol, and we're going to find out why I wrote that in a second. So what do you want to cancel out here? You want to cancel out moles of ethanol, right? So where do you see moles of ethanol anywhere?
Nowhere.
I see moles of ethanol.
Molar mass. Oh.
Will you just use the molar mass? I see it in the combustion, the molar combustion of ethanol. So every 1 mole of ethanol, how much energy is released? Okay, let's look at it from the water's perspective. Is the water absorbing or releasing energy? It's absorbing. So all of a sudden, I know that the ethanol releases energy, but from the water's perspective, the water is absorbing this much energy per mole. Do you agree? Yes. Okay. So there's a phantom negative sign that showed up because of the context of the situation. Okay, what do you want to cancel out? Kilojoules. Well, the energy lost by the fuel is energy gained by the water, right? So what value do you want to use here? The reason why we're not going to use a molar ratio is because is the ethanol reacting with the water in a chemical reaction?
Oh, what's that ratio? I meant like that.
Yeah, okay, good. Okay, that's fine. So kilogram degrees Celsius. Holy guacamole. Moles and moles cancel out. Kilojoules and kilojoules cancel out. What's the only 2 things I need? I need to multiply by the kilograms. How many kilograms of water is this? 0.375 kilograms. And then I also need to multiply by 20 degrees Celsius, right? So I apologize. I couldn't fit it all in one line, but hopefully you understand what's going on. So our kilograms and kilograms cancel out, our degrees and our degrees cancel out, and we should be left with a mass. Fire away.
It's kind of similar to last time, but I'm confused. Why are you adding the temperature to the multiplication to this equation, but the other one we added it?
The temperature, this degree Celsius is always change in temperature. Always change in temperature. So the only way we can get rid of this degree Celsius is with a change in temperature. Do we have a change in temperature? Yes.
So like the last equation we didn't add this ratio, so that's why we had to add the temperature, essentially what you're saying?
The last equation, when we did it, that was in the previous notes package. Okay. The reason why we didn't do it there is because the degree Celsius, that stands for change in temperature. So what we had to do is we had to calculate the change in temperature, then see, okay, if we started here and we're changing by this much, where can we end up at? It's a 2-step problem because this has to be change in temperature only. And a change in temperature you need to either add or subtract from your final or your initial. I don't know any other way to explain it unless we sat down and talked about it. Okay, how much mass? Kelton, did you calculate it?
I got 0.094.
0.0194. You missed.
No, 0.094.
Okay.
I got 1.076.
1.076. That sounds a lot closer. That sounds a lot better. Alicia.
Yeah.
You did 46.8. Oh, that was me. Yeah, that was me.
Oh, in the calculator, people went 46.8.
Yeah.
Oh.
Yeah.
I took an L.
How long have we been using calculators for? 1.05? 596. Boo them, yeah. Okay, if we didn't take into account that negative sign, the negative of a negative, what kind of a mass would we have gotten? A negative mass. So it's fine. It's fine if when you're dealing with that mass as a negative, as long as you understand, well, a negative mass means I must be using up the mass, that kind of thing. Or another way of thinking about it is a negative mass can exist, but it does represent how much I need to use up. That kind of thing, yeah.
So say Mr. Bolton gives us a nice test.
Yeah.
And this test has a question like that.
Yeah.
And it's like, show your work.
Yeah.
So if you use the negative.
If you use the negative all the way up until the very end,
And then you just switch it at the end.
yeah, that's totally fine, because you understand that negative sign has to disappear somehow. Yeah. Okay. The temperature. So far, our only technique has been unit analysis. Kelton, come on. So far, our only technique has been unit analysis. All of these questions, they're all exactly the same. It's just you're either flipping this ratio or you're looking for something different. So the temperature of a 100 milliliter sample of water decreased from this to this when 1.87 grams of ammonium nitrate was dissolved. Find the molar enthalpy of solution for ammonium nitrate. Okay. What are you looking for? The molar enthalpy of solution. And what is molar enthalpy always measured in? Kilojoules per mole. Okay, remember it's kilojoules per mole of ammonium nitrate, right? So, what do you want? What do you want on top? Okay, let's read through the question. Do you see kilojoules anywhere at all?
No.
What do you have to use? You have to use the water. Because the ammonium nitrate, is the ammonium nitrate absorbing energy or is it releasing energy?
It's releasing. Oh, yeah.
Because the water's getting colder, right? And in order for the water to get colder, something inside the water had to absorb that energy. Yeah, okay. So as long as we understand that, so again, the energy absorbed by the ammonium nitrate has to be the same as the energy lost by the water. So I would say 4.19 kilojoules per kilogram degrees Celsius. Okay, now I want to be very clear. The kilogram, what does that kilogram represent? Mass of the water, right? People are going to be so tempted to cancel out kilograms with grams of ammonium nitrate. You cannot do that, right? This represents kilograms of water. So let's cancel out the kilograms of water. How many kilograms of water do we have? 0.1000 kilograms of water. Can we cancel out the degrees Celsius? What does the degree Celsius in this value represent?
The change.
The change. So as long as you have the change, then you can cancel it out. So it's 2.17?
Yeah.
2.17 degrees Celsius. So kilograms and kilograms and degrees Celsius and degrees Celsius. So we're left with kilojoules. We know how much energy was absorbed by the ammonium nitrate. Now we just need to divide it by the number of moles of ammonium nitrate. Do you know how many moles of ammonium nitrate there was here? No, but you have the mass. So you need the molar mass. What's the molar mass of ammonium nitrate? What? First of all, what's the formula for ammonium nitrate? Oh man, 32.
Yeah.
40, 78, 80, 80.06.
Yeah, that's it.
Okay, so we're going to multiply. What do we need on top? What do we want on the bottom? We want moles on the bottom, right? So per 1 mole is 80.06. Is that what it was? 80.06?
Yes.
Grams. And so we need to cancel out grams on the bottom, 1.87 grams. So grams and grams, and we've got kilojoules per mole. Hopefully that makes sense. Kilojoules per mole. And then once somebody calculates an answer for me, then just give it to me just later. 38.92. 926, blah 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 blah. Kilojoules per mole. So there's, I don't know, how many things are wrong with this answer?
Only one. Two.
Ammonium
nitrate.
I don't know. So it should be 3 digits, right? 38.9 kilojoules per mole. But you have to get your negative or your positive from the context of the situation. Did our ammonium nitrate absorb or release energy?
Absorb.
It absorbed it, right? So it should be positive. Strictly speaking, we should always have a phantom negative sign in here. Was the temperature change positive or negative? Did it increase or decrease in temperature? It decreased, but that negative should have been canceled out by a phantom negative when we took into account it was the ammonium nitrate's perspective. So that's why it's positive. Whatever. Okay, so I'm going to splice this video in the middle of me standing up at the front of the class talking because I kind of forgot to do this in class. Silly me. So we've got another example here. A student poured 50 milliliters of a 1 molar solution of sulfuric acid into a beaker containing 50 milliliters of 1 molar solution of sodium hydroxide. So we got an acid and we have a base, and they're going to neutralize each other. When they neutralize each other, they're going to either release energy or they're going to accept energy. So the temperature of the solution increased by 8.5 degrees Celsius. Calculate the molar enthalpy of a solution, of neutralization for sodium hydroxide. So let's just kind of double check we know exactly what's going on here. So we've got a beaker. Oh man, a beaker. That's terrible. And it's containing 50 milliliters of 1 mole per liter. So, the first one is not 1 mole per liter sodium hydroxide. It's 1 mole per liter sulfuric acid. Perfect. And then we've got another beaker. And in that beaker contains 50 milliliters
of 1 mole per liter sodium hydroxide. So we're going to take the sulfuric acid and we're going to pour it into the beaker containing the sodium hydroxide, and we're going to observe a temperature change. Now, the temperature of the solution increased by 8.5 degrees Celsius. That means, though, the water gained energy. So if the water gained energy, then our chemical system, the combination of sulfuric acid and sodium hydroxide, they reacted together. So when they rearranged their atoms and their bonds, they must have lost energy. So we know we're going to get a negative molar enthalpy a little bit later on. Okay, enough chit-chat. Let's do this. So a student poured this much of that solution into a beaker containing this much of that solution. The temperature increased by 8.5 degrees Celsius. Calculate the molar enthalpy of neutralization. So that means molar enthalpy of neutralization. We kind of read it backwards. And it's measured in kilojoules per mole. And we're talking moles of sodium hydroxide because we want to relate it back to sodium hydroxide. Okay, no problem. So I'm going to look for kilojoules. I don't see kilojoules anywhere in here, but I do recognize that we're heating up water. Water's gaining energy. And so whenever water gains energy, it gains 4.19 kilojoules for every kilogram of water degree Celsius. So for every 1 degree Celsius that a kilogram of water wants to go up in temperature by, 4.19 kilojoules has to be gained. So what do we want? Well, we want to keep our kilojoules, and we want to get rid of every other unit other than kilojoules per mole of sodium hydroxide. So let's multiply that by the mass of water, right? We want to get rid of kilojoules or kilograms of water, so let's multiply by the mass of water. Well, what's the mass of water? When we pour this into here, what's the mass of water? Yeah, it's going to be 50 plus 50 is going to be 100 milliliters, right? So 100 milliliters is 0.100 kilograms of H2O. So kilograms and kilograms will cancel out. Let's cancel out the temperature, degrees Celsius, so that's easy. We had a temperature change of 8.5 degrees Celsius, no problem. So what's happening here is kilograms of water, degrees Celsius, degrees Celsius. The only thing that we have to worry about is we want per mole of sodium hydroxide. Well, do you know how many moles of sodium hydroxide are here? Well, we know that in every 1 liter, here, there's 1 mole. So where do we want to put our moles? We want to put our moles on the bottom. So 1.00 moles per 1 liter, and this is of sodium hydroxide. So we want moles of sodium hydroxide on the bottom, moles of sodium hydroxide. So all we have to do is cancel out how many liters. How many liters of sodium hydroxide did we have? Well, we had 0.0500 liters of sodium hydroxide. Oh, I'm running out of room. Uh-oh. So all we have to do is go ahead and do this calculation, but I just want to prove to you that we're going to get the units we need to. Liters of sodium hydroxide, so we're going to be left with moles of sodium hydroxide on the bottom. Going to be left with moles of sodium hydroxide on the bottom and kilojoules on top. That's exactly what we wanted, so I know I'm going to get the appropriate answer. When I put all of this into my calculator, I end up getting a number of 71.23 kilojoules per mole of sodium hydroxide. There's a couple things wrong with this, though. Can you figure it out? Can you figure out what's wrong with this? One thing might be pretty obvious. Yeah, 3 digits, 2 digits, blah, 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 blah. So we need 2 digits. Okay, so this is really going to be 71 kilojoules per mole of sodium hydroxide, no problem. But also, what did we say happened to our solution? The water gained energy, right? The temperature increased. So if the kinetic energy of the water goes up, then that means the potential energy of the mixture had to go down, because you can't both gain energy. If something gained energy, something else had to lose energy, right? So that's our problem right there. So we got negative 71 kilojoules per mole of sodium hydroxide. Okay, back to class. Watch this transition. Whoa!
Yeah. Okay, Mr. Brown's gonna be here tomorrow. I expect you to treat him better than you treat me. What?